The next type of matrix is Hermitian matrix. It is the type of matrix in which contains the complex numbers and the trans complex conjugate of this matrix and transpose. If you take the complex conjugate of each element, and after that if we take the transpose of that matrix, then it should be equal to the original matrix A. So in the case of Hermitian matrix, it should contain the complex number. For example, 5, 1 minus I, 1 plus I, 5. So this is just an example of Hermitian matrix, 2 by 2 Hermitian matrix. So let's say for example this matrix is A. Now if I calculate the A complex conjugate of matrix A, it means I need to take the complex conjugate of each element. So since it is a real number, so it will be as it is, and complex conjugate of 1 minus I will be 1 plus I, complex conjugate of 1 plus I will be 1 minus I, and 5 again it will remain same. If I take the transpose of this matrix, then it will be equal to 5, 1 plus I. So here this row I am writing as a column, 1 minus I and 5. So we can see this matrix is equal to this. So when it satisfies this condition, in this case the matrix is called the Hermitian matrix. So one important point here to note is in Hermitian matrix, diagonal elements are always real. The diagonal elements cannot be complex here. The next matrix is skew Hermitian matrix. So in this case, the complex conjugate transpose of the matrix will be equal to minus A, or in other words, Aij is minus times of Aji. Similarly, in the Hermitian also we can write it as a Aij is equal to Aji complex conjugate. Here also it will be a complex conjugate. So example of this type of matrix is 5 minus 1 plus I, 1 plus I, 5. So in order to check this matrix, first of all I will take the complex conjugate of each element. So it will be 5 minus 1 minus I, 1 minus I. Here just I am replacing I by minus I in order to take the complex conjugate of each element. Here if I take the transpose of this, then it will be 5 minus times of 1 plus I minus times of minus 1 plus I and 5. So here I have taken this example intentionally to understand that how the diagonal elements should be in the case of skew Hermitian matrix. So here we can say that if this term, if I am taking the negative out of this, then only it is going to become minus a. So in this case, the diagonal elements cannot be a real number. It should be either a zero. Let's say, for example, let me modify this example. If this element would have been zero, then a bar transpose can be written as minus times of 0, minus 1 plus I, 1 plus I, and 0. So you can see this A matrix is equal to A bar transpose minus times. So in the skew Hermitian matrix, diagonal elements should be either 0 or it should be purely imaginary or purely imaginary. And the reason is quite clear here. 0, we have seen one example with 0. Let's consider if any imaginary number would have been coming here. So if I take the complex conjugate, it will give a negative sign, and again negative I need to take out of this. So finally it will become the skew Hermitian matrix. So the diagonal element should either be 0 or it should be purely imaginary. Let's move to the next type of matrix, which is called idempotent matrix. If any matrix A satisfy this condition, A square is equal to A, then it is called idempotent matrix. The next is nilpotent matrix. If A to the power k is equal to 0, 0 means null matrix, where k can be any positive integer. So let's say, for example, A square is equal to a null matrix or A cube is equal to null matrix, then it this kind of matrix is called the nilpotent matrix. So now we have seen the various types of matrices. Now I'll talk about the addition, subtraction, and multiplication of matrix, which we already know as such. So let's start with the addition of matrix, addition and subtraction. So let's consider one matrix with the elements A1, B1, C1, and D1. Suppose I want to add this to or subtract another matrix A2, B2, C2, or D2. So the important thing here is whenever we are adding or subtracting two matrices, the order should be same. So here the 2 by 2 matrix, and this is also a 2 by 2 matrix. So the resulting matrix will be A1 plus A2 if you are adding, and if you are subtracting, then it will be A1 minus A2. That's what it means. This will be B1 plus B2 or B1 minus B2 based on addition or subtraction. Similarly, C1 plus minus C2, D1 plus minus D2. So the rules of adding or subtracting the matrix is order should be same, And another important property is addition is cumulative. It means A plus B will always be equal to B plus A. And it also, we can also apply associativity. So this is associative. So A plus B, if I add the two matrix and then I'll add it to the third matrix, this will be equal to the addition of first matrix with the summation of remaining two. And it can also be written as B plus C plus A. So this is a quite general thing which we already know. Now another just a review of the multiplication of matrix. For matrix by a scalar. So first I'll talk, if I multiply any matrix by a scalar, what will happen? So in this case, every element of the matrix get multiplied by that scalar. So let's consider A, B, C and D. If I am multiplying a scalar K, then the resulting matrix will be Ka, Kb, Kc, Kt. The next I will move to the multiplication of matrices. If suppose I want to multiply two matrices, multiplication of matrices. So if suppose I have a matrix A whose order is m by n, m is the number of row and n is the number of column, and I have another matrix B which has the order n by p, n rows and p columns. So if I want to multiply these two matrices, then in which case I can multiply? So the rule says that when this will be same, it means the columns, number of column in the first matrix should be equal to the number of rows in a second matrix. Then these two matrix A and B can be multiplied, and the resulting matrix order would be m by p. So this will be the order of resulting matrix. So let's consider one example here. Suppose I want to multiply 1, 2, 3, 4, 5, 6. So this matrix I want to multiply it with 2, 3, 5, 6, 8, 9. So whether we can multiply this matrix or not. So what is the order of this matrix? I will see 2 rows, 3 columns, and the order of this matrix is 3 by 2. So yes, I can multiply these two matrices and the resulting matrix order will be 2 by 2. So how to multiply that we already know. So first element will be multiplied by this, so 1 into 2, and the second element of the first row will be multiplied by the first column of sec first by the first column of this matrix, so corresponding element 2 into 5 plus 3 into 8, and so on. We can do the remaining part. Again we'll start with the first row, so 1 into 3 plus 2 into 6 plus 3 into 9. Now next is 4 into 2 plus 5 into 5 plus 6 into 8. Next is 4 into 3 plus 5 into 6 plus 6 into 9. So that's how I can get resulting matrix order is 2 by 2. Now another important thing which is very basic, that is the determinant. So determinant is an expression which is associated with the square matrix. So let's consider a matrix A with element A11, A12, A21 and A22. So this is the matrix. If I want to find out the determinant of this matrix A, which is denoted by like this. So this is nothing but A11, A12, A21, A22. So this is just a cross multiplication. So A11 into A22 minus times of A12 into A21. So determinant of any matrix will be a number which can be obtained by multiplying A11 to A22 minus times of A12 to A21. Another important topic is minor and cofactors. Minors and cofactor. So first we'll talk about minors. What is the meaning of minor with respect to a matrix? So let's consider a matrix A, B, C, D, E, F, G, H, I. So this is a matrix of order 3 by 3. So the minor of this matrix is nothing but I can form a determinant by deleting certain rows and columns. Let's say for example if I delete this row and this column, so then I'll get EF HI, and if I put it in a determinant format, so if suppose I'm considering this element and the element corresponding to this row and the column corresponding to element A, so this is called the minor of A. It is nothing but element A11. So minor of A, which is nothing but the minor of A11, which can be obtained by deleting the corresponding row and corresponding column, and after that whatever elements we need to form a determinant, and this determinant will be EI minus F into H. So this is called the minor of A11. Similarly, we can find the minor with respect to each element. So when we delete one row and one column corresponding to any element, then the minor formed by this is of the second order. So this is called minor of order 2 by 2. So generally whenever we take any matrix of order 3 by 3, then we can start with a minor of order 3 by 3 without deleting any row and column. So third order minor, if I write third order minor of this matrix is nothing but the determinant of original matrix itself. In general, whenever we talk about the minor and in the earlier classes in the school level, whenever we have seen the minor, we generally talk about the 2 by 2 order minor only. But the basic meaning of minor can be understand in the sense of a subset. If I am taking any matrix of order 3 by 3, then I can have the subset of this matrix itself, and it is with respect to minor we take always the determinant. So one determinant can be obtained without deleting any rows and any columns. Then the second order minor one example which we already discussed. So with respect to A11, we talked about the minor. Similarly, we can go corresponding to all the 9 elements. So second order minor, there will be total 9 minors will be there of order 2. And first order minor, so the first order minor we can obtain by deleting the 2 rows and 2 columns. So if I am considering the element A, then I can delete this 2 rows and the 2 column corresponding to this, then I'll be getting I. So if I do one by one for all the 9 elements by deleting 2 rows and 2 corresponding columns, then I'll get total 9 minors again. So now in this way we can understand that if any matrix of order 3, then there will be one minor of order 3, there will be 9 minors of order 2, and there will be a 9 minors of order 1. This will be a very important thing when we will be talking about the rank of the matrix. In order to understand the basic from the minor point of view, it will be very helpful in the next subsequent topics. So the next is the cofactor, and cofactor is nothing but the minor with a proper sign. Minor with proper sign is called the cofactor. So if I take again the cofactor of A, or the element A11, I can call it first row first column. So cofactor of this element will be nothing but minus 1 to the power 1 plus 1 minus 1 to the power I plus j. So 1 plus 1, here I is 1, j is 1, and the minor. So when I take this A, so EF I, so EF H I. So this will be called the cofactor of A. So one by one we can calculate the cofactors of each element and can form a cofactor matrix. So this can be written as A11, or let's say C11, cofactors corresponding to first row and first column element. So similarly I can calculate C12, cofactors of first row second column, so that is B, and so on. I can calculate up to C33. So the cofactor matrix is represented by matrix can be written as C, that is nothing but C11, C12, C13, C21, C22, C23, C31, C32, C33. So that's how we can find the cofactor matrix. The next is adjoint of a matrix. So what do we mean by the adjoint of the matrix? So adjoint of any matrix A is nothing but the cofactor matrix transpose. So as we have earlier denoted cofactor matrix by C. So once we find out the cofactor matrix and when we take the transpose of this matrix, then it is called the adjoint of matrix A. And it is important in calculating the inverse of the matrix. So the inverse of a matrix we can find out the inverse of any matrix, which is denoted by A inverse. This is equal to adjoint of A divided by the determinant of that matrix. Now I'll take a simple example and I will try to explain cofactor, adjoint, and the inverse of the matrix. So let's consider this example, any matrix of order 2 by 2. Let's consider A, B, C, and D. This is a 2 by 2 matrix. So here my objective is to find the inverse of this matrix. So inverse will consist of adjoint, and in order to understand the adjoint we need to know the cofactors. So everything will be clear with this by understanding this example. So let's find out the cofactor matrix first. So one by one we need to find out the elements of the cofactor matrix. So cofactor of A11. So A11 is the first row first column element A. So if I want to calculate the cofactors, so cofactor of any element Aij is given by minus 1 to the power 1 plus 1, and deleting the rows and columns corresponding, so I am getting D. So this will be positive D. Similarly, cofactor of A12 can be given as minus 1 to the power 1 plus 2. So first row second column, so if I delete this then I'll be getting C, but here it will be a negative sign. Similarly, cofactor of A21, so A21 I'll be getting the B element and minus 1 to the power 2 plus 1 B minus B. The cofactor of A22 will be equal to minus 1 to the power 2 plus 2. I'll be getting here A. So A. So I got this element as a C11, C12, C21, and C22. So these are the cofactor matrix element. So I can form the cofactor matrix now, which is given by C. So I can write down all the elements C11, C12, C21, and C22. So if I write all the elements, then it will be D minus C minus B and A. Now the next is I need to find out the adjoint in order to find out the inverse. So adjoint of matrix A is nothing but the C transpose. So if I take the transpose of this matrix, then it can be written as D minus C, then minus BA. So, and the determinant of this matrix, original matrix A, is A into D minus B into C. So the A inverse is nothing but adjoint of A divided by the determinant of A. So it will be nothing but 1 upon AD minus BC, D minus B minus C to A. So this will be the inverse of this matrix. So whenever we find the inverse of any matrix, it is very important point that the determinant A of A must be non-zero. Otherwise, the inverse of the matrix is not possible.